Alright, in this figure we've got the net of a dodecahedron. Now a dodecahedron is just a polyhedron with 12 faces, alright? And you can, it's in Latin essentially right here. Do, 2, and dec is short for 10, so dodeca is 12, is a 12-faced hedron, polyhedron, which is a three-dimensional solid figure. Okay, so we have a 12-faced three-dimensional solid figure that we've sort of essentially cut apart at the seams and laid flat. Okay, that's what a net is. So it's sort of like the two-dimensional version of the three-dimensional figure, the three-dimensional polyhedron. Okay, so this is sort of the flat version. So if we were to like cut this apart, cut this out, and then fold it along the edges and join the edges up, we would end up with a three-dimensional solid figure, which would be a dodecahedron because it has 12 faces. Okay, so and in this regular dodecahedron, 3 edges come together at each vertex. So for example, here's a vertex. Now 2 of the edges are already connected, and then these 2 edges up here, if I highlight those, you can see that if we fold this up, these 2 edges are going to come together and make one edge. Okay, so you can see we have 1, 2, and then 3 edges that come together at each vertex. Okay, and when the net is put together, the solid has x vertices and y edges. What is the value of x plus y? Alright, well first of all, I'm going to change these variables because x and y really aren't very meaningful. I'm going to call this v and I'm going to call this e. Okay, because v for vertices and e for edges, just it seems like it makes sense. It's self, it'll be easy to remember what those variables mean. Whereas if I call it x and y, then I'll be like, okay, now what was x? How did I define x? I can't remember. But if I call it v for vertices and e for edges, then it'll make more sense to me. All right, so you can see this is basically, we have 12 pentagons here, 12 regular pentagons, and we put them all together and we can form a dodecahedron. All right, so and every pentagon has 5 edges, right? So if we took 12 pentagons times 5 edges per pentagon, then that would give us the number of edges of the total of all the individual pentagons, right? But we actually, when we put this together, every edge meets another edge. So every 2 edges become 1 edge in the dodecahedron. Okay, so we have to divide this by 2 to get the number of edges in the dodecahedron, right? Because we're going to join every 2 edges into 1 edge in the dodecahedron. Okay, so this is going to give us the number of edges. So we just take the number of edges in in each pentagon times the number of pentagon, and then recognize that every pentagon touches another pentagon and the edges meet to form 1 edge. Alright, so that gives us essentially 6 times 5, which is 30. Okay, so we have a total of 30 edges. And there's a couple of different ways that you can figure out the number of vertices. One way, if you happen to remember Euler's formula, that says that the number of faces plus the number of vertices minus the number of edges is equal to 2. So we know the number of faces is 12. The number of vertices is what we're trying to find, and we just figured out the number of edges, and that's equal to 2. So we can solve for the number of vertices if we add 30 and subtract 12 from both sides of the equations. We end up with v is equal to 20. Okay, so that's one way to find the number of vertices. And you can see that if we added 30 edges and 20 vertices, that's what we're looking for, so that gives us 50. So, but I'll tell you, I'm not very good at remembering formulas. So if you happen to remember that, that's good. I would rather reason it out. So here's the way I did this problem. I said, well, okay, three edges meet at a vertex. So if I took the number of vertices times 3, so I take the number of vertices times 3. So every vertex meets 3 edges, right? So for every vertex we have 3 edges, but every edge connects 2 vertices. Okay, so every edge connects 2 vertices. So if we divide that by 2, this is another way of getting the number of edges. Okay, and that should be 30. Okay, does that make sense? So I've got the number of vertices times the number of edges per vertice that meet at that vertex, and divided by 2 because we have 2 vertices per edge. Okay, so you can see every edge connects 2 vertices. Okay, so if I just took the number of vertices times 3, I would overcount because I would count. So I would count for this vertex. I'd count 1, 2, 3, but then for this vertex, I'd end up double counting this edge. Okay, and I would end up doing it for all of the vertices. Okay, so I had to divide by 2 because it takes 2 vertices to make it to connect into an edge. Okay, so I can use this to figure out the number of vertices. So if I divide by 3 and multiply by 2, then I get the number of vertices is equal to 20. Okay, so to me, I can never remember formulas, so I would rather reason it out like this. And then, like I did before, the number of vertices plus the number of edges is equal to 50. Okay, 30 plus 20. So there you go.